today we are left with one last thing in this unit, that is silicates. So silicates also come into the category of these condensed molecules where discrete unit of silicon tetroxide, which is a tetrahedron molecule, condenses and shares oxygen atom. They're sharing up the corner of the tetrahedron between different units, and they generate all sorts of straight chain compounds, cyclic compounds, or dimeric or oligomeric compounds, and then one dimensional chain, or two-dimensional sheets, and then ultimately a 3D network also, which is an example of the silica, perfect example of a tetrahedron spreading its bonds in all the directions in three dimensions and generating a 3D network. When we started this unit, when we started discussion on d pi p pi bond, and we discussed that silicon oxygen bond, though it is not written as a silicon oxygen double bond, but it has extreme strength, and that strength has been attributed to the not it's not a pure single bond. There is significant contribution from the overlap between the 3D orbital of the silicon and 2p orbital of the 2pz orbital of the oxygen atom, and that strength, the strength that silicon oxygen bond derives is attributed to the d pi p pi bond, and because of that extreme strength of this silicon oxygen bond, the silicates are so abundantly found in the Earth's crust that silicon and oxygen contribute, along with the aluminum. About 90% of the Earth's crust is formed by these three elements. So the structural chemistry is diverse, and most of these compounds are insoluble in water, silicates. That's why there was problem with the structural characterization, because they could not be precipitated, they could not be splitted into simple compounds, and they were present in only solid state. And until the X-ray crystallography became available as a tool of structural characterization, the structural details of these compounds were not known, though they were so abundantly prevalent around us in different forms, in the gemstones, as the clay, as the ceramic materials, all of them, even cement. You talk of any material, bricks, everything contains granite, micas, and all the clays, all sort of clays. Even gemstone contains silicates, but then the structural details were not available until we found X-ray crystallography as a tool to characterize the solid materials, particularly crystalline materials. Then it became then the silicates were characterized, and different types of silicates were classified, and different structural modifications were identified. So let us go to the new presentation. Oh. Is it visible?
Yes, sir.
Yes, sir.
Okay. So the chemistry of silicates is dominated by silicon. Chemistry of silicon is dominated by the silicon oxygen bond, and for obvious reasons, that this is a bond which is extremely stable, and therefore because of its strength, silicon has a strong tendency to form the silicon oxygen bond. So basic unit of silicon oxygen is silicon oxygen tetrahedron, which has four oxygen atoms directed towards the corner of a regular tetrahedron, and each oxygen atom, because oxygen is always divalent, and we say that each oxygen atom carries a negative charge, and we have SiO4, 4 negative. So 95% of the Earth's crust contains silicate minerals, aluminosilicates in the form of aluminosilicates and clays and silica, granite, slates, bricks. You talk of any material, cement, ceramic, and even glass, they all contain silicates. So these are some examples. Olivine, this is divalent metal ion linked with the simple silicon, silicon tetroxide. The simple silicates are very rare. They are very few, which contain the discrete silicon tetra or silicon tetra, tetroxide tetrahedra. Then the pyroxenes, there's another class of silicates in which we have the uh, the chain-like structure or dimeric or trimeric structure, and the general formula is SiO3, where one of the oxygen atoms is shared between the two tetrahedras. This is a dimer, and it contains how much charge? It should contain six negatives. So this should be Mi3, a metal in the three oxidation state. Then amphiboles, these are aluminosilicates. These are chain-like structures we'll talk about later on. These micas, these are different alkali metals, magnesium, iron, and silicon, silicates 3. Orthocase feldspar, this is potassium aluminum silicate. Then muscovite micas, potassium aluminum, different. This contains OH group also. Then quartz, SiO2, zeolites, they contain sodium aluminum silicates, different compounds. These three are constituents of granite: orthocase feldspar, muscovite micas, and quartz. They are ingredients in components of the granite. So first we talk about the soluble silicates. There are very few, as I said earlier. By and large, silicates are insoluble in water, because that's why they are parts of rocks, clays, and other materials. The which is present in the earth, because they are insoluble in water. But the first class is that your monomeric unit, then that is, it's not a polymerized, it's not dimerized unit, then it is water soluble. So how it is water soluble silicate is formed? If you fuse sodium carbonate with sand, and in an electric furnace at a very high temperature of 1400 degrees Celsius, you get carbon dioxide plus sodium silicate, the monomeric discrete unit, and then different oligomers of this sodium silicate, where SiO3 may N means 2, 3, 4, 5, and others. The melts of the variable composition is formed, and these are water soluble. So water soluble is this, particularly this sodium silicate is water soluble. Solution of sodium silicate, when you dissolve it in hot water under pressure, it becomes water soluble, and that is known as water glass. A variety of uses for years. This sodium silicate, this soluble sodium silicate, has been used for years. For example, it is fireproofing agent. You paint it, use it in paints, the paints become fireproof. Then sizing of paper, you can use it as a glue, and you can paste papers, and you can preserving eggs, and then its solution is slightly acid, high, higher, having high density than water. Therefore, it's an excellent medium for growing crystals, slowly, and large crystals grow, because crystal growth requires a viscous medium, and disturbance should be least during the growth process. So because it is slightly denser than water, it allows the crystals to grow very slowly if there is no disturbance to the solution, and therefore large and beautiful crystals grow slowly. That's why it is known as chemical garden, because it's used for the growth of the crystals. in good, large crystals. So that is sodium silicate dissolved in hot water under pressure. Composition varies, but approximately it is written as sodium silicate is set of dimer. Sodium, it should have been here Na4. Na4 Si side 2O5, yes. A dimer will have Na6, not 4, Na6. Liquid, it is also used as an important component of liquid detergents because to keep the pH high, sodium silicate is acidic, and when it is acidic, acids will dissolve fats and greases uh, from the clothes. But if the water is hard, then this sodium silicate should not be used because it forms an insoluble precipitate with calcium as a calcium silicate, and that will spoil the functioning of the liquid detergent. Therefore, it has to be used with caution that water should not be hard. So, principles of silicate structures. Majority of the silicates are insoluble, which contain infinite ionic structure because and strong silicon oxygen bonds. So there was difficulty to characterize them structurally because of the reason that they are not soluble in water and they are diverse structures, different compositions. The physical properties were, however, studied for a long period of time until and unless XRD became available, and XRD solved the structural mystery of all silicates because X-ray is the final proof. It's just like a photograph of bones. X-ray also gives a photograph of the crystal solid structures, indicating not only giving information about the bond lengths and barnacles, but also the orientation of the bonds in space, how different tetrahedras are joined together in different orientations to give the different structural features of the different silicates. So electronegativity difference between oxygen and silicon, oxygen 3.5 and silicon 1.8. So difference is 1.7. So it's not going to be a 100% covalent bond. The electronegativity difference is huge. So we expect this bond to be 50% ionic and 50% covalent. So both theoretical models which are being developed for the ionic bonding as well as models which have been developed for the covalent bonding, both are applied, separately. Both can be used to study the silicates. So ionic and covalent models, theoretical models can be used. For example, the ionic model talks in terms of the radius ratio, that if the radius ratio is in a particular range, the coordination number will be decided. If the radius ratio is less, then the coordination number is less. If the radius ratio increases, that is, as the size of the cation increases as compared to oxygen, as compared to anion, then the coordination number increases. So this is based on the fact that if you presume that the bond between silicon and oxygen is 100% ionic, so the radius ratio concept guidance can be used to predict the coordination number of the metals. And on the other hand, the covalent bonding talks in terms of the overlap between orbitals and central atom. Silicon has one s orbital and three p orbitals, just like carbon atoms, and there are four electrons, and it is absolutely ready to form four covalent bonds, and the hybridization will be sp3, and therefore the four bonds will be directed towards the corners of tetrahedron. So we can have the silicon oxygen bonds, four coordination number, tetrahedron. Radius ratio also talks about the four coordination number for silicon because the radius ratio falls in the range of 0.29, and for which the predicted coordination number is 4. So 3s and 3p orbitals for silicon bonding, and SiO4 tetrahedron unit is a discrete unit in terms of the covalent bond. So silicon tetroxide unit is a discrete unit, or it can polymerize by sharing or a corner, or for sharing an oxygen atom. Oxygen atom becoming the bridge between at least two tetrahedra, and you can have the polymerization. One oxygen atom making bridge, so you can form a dimer. So another oxygen atom forming bridge, it can form a chain. So chain can grow on and on, right, having different repeat units. We'll talk about that later on. So the oxygen atoms, according to the ionic model, the oxygen atoms form a closed Baker arrangement, hexagonal closed Baker arrangement or triple closed Baker arrangement, depending upon the situation. And then we have tetrahedron or octahedron holes, and metals will occupy that silicates or contain invariably the metal also as a counterions: sodium silicate, potassium silicate, aluminum silicates, and calcium magnesium silicate. Sometimes there is single metal, sometimes there are combination of metals available in silicates. Just as the example we give here, there's aluminum silicate, this magnesium iron silicate, it's potassium aluminum. So there may be single metal or combination of metals as the counterions. So these metal ions may occupy either tetrahedron holes, voids, or octahedron holes, depending upon their size and the coordination number which satisfies them, right? So sometimes the metals are occupying the tetrahedron voids, sometimes they may be occupying the octahedron voids, depending upon their size. So most metals can fit in any one type of the holes. Aluminum is a metal which can fit either. It can either occupy tetrahedron holes or the octahedron holes. So aluminum can replace either metals. So many times we get different silicates by replacement of the metal ion by another metal ion which is having same size and same charge. That these are the two requirements for replacement of one metal by another metal. That metal should have same size and it should have the same charge. So aluminum, because it can occupy either octahedron or tetrahedron void with ease, so it can replace a metal which is already in the tetrahedron void, or it can also replace a metal which is in the octahedron void. Therefore, we have the aluminum is the most dominant or most prevalent atom in silicates. Aluminum can fit it, or aluminum can replace either metal in one hole, any one of these holes, and it can also replace silicon atom in the lattice. That's another diversification, that aluminum can replace not only the counter ions which are occupying the tetrahedron or octahedron voids. It can also replace silicon. It resembles silicon in its size, and it can replace silicon from the lattice side. So sometimes sodium and potassium can have coordination number 8 and lithium coordination number 6 rather than 4. Similarly, sodium and potassium, as per the radius ratio, they are expected to have the coordination number 6, but sometimes in silicates they can have coordination number 8. Similarly, lithium is expected because it's small size metal. Radius ratio is very small with radius ratio of lithium with oxygen, oxide anion is small. So we expect coordination number to be 4, but in many silicates it is having the coordination number 6. So that is deviation from the radius ratio rule. So the conclusion is that radius ratio rule is only a guiding principle. You cannot apply radius ratio rule strictly to the silicates because silicates are not 100% ionic. There's charge separation between silicon and oxygen is not 100%. You don't have silicon 4 positive cation and oxygen 2 negative anion. We don't have that situation because silicates are partially covalent and partially ionic. So you cannot apply the radius ratio rules with full strength. There is no, there are always deviations, and there are always, exceptions, because these rules will be violated because the bond is not 100% ionic. Now, classification, the manner of these tetrahedron units are linked together. That's the basis of the classification of the silicates. And first class is orthosilicate. Just as we had the orthophosphates, phosphoric acid was also called orthophosphoric acid, and the phosphates which were derived from the orthophosphoric acid were called orthophosphates. They are also known as silicates. Orthosilicates contain discrete SiO4 negative tetrahedron unit. For example, M2 second SiO4. This is 4 each metal ion. metal example, calcium 2 plus, magnesium 2 plus, iron 2 plus, zinc 2 plus, this sort of situation, beryllium, magnesium, iron, manganese, and zinc. Or so you can have simply zirconium silicate, single metal, having 4 plus charge and satisfying, acting as a counter ion to the silicate anion. So different structures depending upon the coordination number of metal. So it depends upon what sort of coordination number the metal is satisfied. What is the charge of the metal ion? What is the size of the metal ion? Which particular void is it occupying? Is it occupying a tetrahedron void or octahedron void? So that decides the different types of structures. So this is williamite, zinc to silicate phenomasite. This is beryllium silicate, both having coordination number 4. So beryllium and zinc occupying the tetrahedron holes. Forsterite, this is magnesium silicate, coordination number 6, and magnesium occupying octahedron voids. Here is the radius ratio: beryllium, magnesium 0.25, silicon oxide 0.29. So coordination number for silicon is 4, beryllium is also 4, aluminum, it is coordination number is 4.2. So coordination number radius ratio is 0.42. So it's a borderline case, and coordination number can be either 4, it can be also 6. That's why the aluminum has the tendency to occupy either octahedron or tetrahedron voids. It can replace any metal ion which is present in the tetrahedron void or the octahedron void. Magnesium oxide, the radius ratio is 0.59, so we expect coordination number 6. Iron 2 plus and oxide, radius ratio is 0.68, so we expect coordination number 6. So this is discrete tetrahedron. It's also in a symbolic mirror represented by a triangle where silicon is at the center of the triangle, 3 oxygen atoms are at the corners of triangle, and 4th oxygen atom, which is pointing out above the plane of this triangle, is drawn as a circle around this silicon atom. So metals in the octahedron sites can be replaced easily by other metals without changing the structure. So basic structural feature remains same. Physical properties change. For example, color changes in silicates by when you replace one metal by another metal. Say you add chromium, it gives green color to the gemstones. So, but the structure remains same. For example, mineral olivine contains magnesium, iron, silicate, has same structure as forestite, but 1/10 of the magnesium ion in the forestites are replaced by the iron atom. So iron and magnesium, as we see here, have almost same size. The iron atom has 0.72 and magnesium 0.72 angstrom, and iron atom 0.78. So they can replace each other. They have also same charge. So charge and size are proper that the iron can replace magnesium. So you can add manganese also. So you can have a combination of the calcium, magnesium, iron, and manganese. So it's a non-stoichiometric compound. So 0.5 this, say 0.2 this, 0.3 this, then silicate. Hexagonal close packing is adopted by this molecule, by this mineral. So then we have zirconium silicate, also a monomeric compound. It's a gemstone cut to look like diamond. This is colored compound, and it looks like a diamond, but is much cheaper than diamond, softer than diamond. Therefore, cut edges, they lose their sheen, and they become rough over a period of time, and therefore it loses its sheen. Cut edges make gemstone attractive, eventually wear and spoil the look of the stone. Zirconium, the coordination number is 8 for zirconium here. Then garnet is another gemstone, discrete tetrahedron, large crystals of garnet cut and polished and used as red gemstone. Same, silicate garnet is also used as an important component of sandstone. It is grinded and pasted on the paper, and you get sandpaper, or smoothing the rough surfaces. That this contains magnesium, metal in the divalent state 3 times, metal in the trivalent 2 times, and silicate 3 times. So the divalent metals are magnesium, calcium, iron second with coordination number 6, and trivalent metal ions are iron 3, chromium, aluminum, and coordination number is 8. Then the second one is pyrosilicates. Pyrosilicates are when two tetrahedrons join together uh, and share an oxygen atom, we get a dimer. Those are known as disilicates or pyrosilicates. Just as in the case of phosphorus, we had pyrophosphoric acid. So remember H4P2O7, and the salts were the Na4P2O7, sodium pyrophosphate. Similarly, we have pyrosilicate, silicate SiO4 sharing one oxygen atom, and you will have SiO7 now. Because one oxygen atom is shared, the charge on each unit is -3 and -3, so it is 6 negative. So this is the structure that you have one oxygen atom, one corner of the tetrahedron shared between two tetrahedrons. So unit is Si2O7 6 negative. So pyrosilicates, they are rare. uh, Thorbitite. This is scandium, disilicate. A number of lanthanides also form disilicates. Example with the general formula LiN2, because this is 6 negative and the lanthanides are 3 plus. So 2 times lanthanides and Si2O7. But then silicon oxygen bond, this should be 180 degree if it's a tetrahedron. It is 180 degree in the case of scandium compound, but it varies from 180 to 1 goes down to 133 degree in the case of different lanthanides. So the structure is not same as in the case of this scandium compound. So lanthanide silicates, disilicates are not having same geometry. So coordination number for the metal varies also from 6 to 7 and to 8 as the size among the lanthanides increases. So the coordination number also increases. So then we have zirconium silicate, disilicate. This is known as hemorrhite. No difference in the silicon oxygen term. So this is a compound which is ambiguous, which is misleading, because if this is having this type of disilicate as an anion, there should be different two types of bonds. One is this bridging bond, and one is this others are these terminal bonds. So terminal bonds and bridging bonds should have different length and strength. So there is no difference in the length and strength of these terminal and bridging bonds in this zinc compound. So therefore, it is misleading. The structure may not be this one. It may be zinc linked with the zinc tetrahedron, one zinc tetrahedron linked with 3 oxygen atoms and an hydroxy group. It's sharing with its corners with the oxygen SiO4 tetrahedra and giving us a 3D network. And we are taking it an example of zinc 4 disilicate, but actually it is not a disilicate. It has monomeric units linked, sharing this edge with this unit. This is at the center, and each oxygen atom is linked. Zinc is linked with 3 oxygen atoms, and these 3 oxygen atoms are then linked with the silicon tetrahedra, 3 silicon tetrahedra, and fourth one is position is occupied by the OH group. So this is a different type of structure. It is not a simple disilicate. Then we have cyclic silicates, which in which 2 oxygen atoms per tetrahedron are shared. So we have a general formula. You get a ring structure, and general formula is SiO3 n times 2n negative. So smallest ring will be when n is equal to 3 members. Then you have 4, 5, 6 tetrahedral units on, can join together and form a ring silicate. But most common, which are observed, which in the naturally occurring silicates, is हेलो हाँ जी नमस्कार कौन हाँ जी कौन हाँ हाँ संदीप भाई कैसे हैं आप हाँ हाँ संदीप जी बोलिए बोलिए। अच्छा ये वाला, ये केमिस्ट्री डिपार्टमेंट जो किया था। अच्छा मैं मैं संदीप जी अभी क्लास में हूँ, मैं अभी हेड से बात करूंगा, आपको कॉल बैक करूंगा। ठीक है। ओके ओके ओके। राइट। सो साइकिल, हाँ चलिए चलिए। वो फिर दोबारा ज्यादा है कि 10%। तूने ऑथर्स के नाम नहीं हटाए थे? ऑफिस के नाम मैंने हटाया नहीं, मैंने क्यों पागल, वही तो मैंने तुझे फोन पे कहा जब मैंने देखा ना, उन्हें सिर्फ फार्मूला बोले, सिर्फ फार्मूला। अच्छा मैंने कहा कि नहीं अब ठीक है 10% तक तो अलाउड है। हाँ एडीपी को मैंने डीआरपी दिखा था, मैंने एडीपी कर दिया। यार मैंने कल उसको दोबारा मारियो को ईमेल की थी तो कोई जवाब नहीं आया। सर क्या मैंने करूंगा, कल ही किया था, आज दोबारा करता हूँ। हमने किसके रेफरेंस से उधर गए थे हम? इसको आज मैं करता हूँ गुरजसप्रीत को, उसको बोलेंगे आज मैं अभी थोड़ी देर में बोलूंगा कि शाम को वो करेगा। शाम को ही वहाँ दिन होता है ना। हाँ। पहले भी एक दिन मैंने उससे कराया था, तो उस वक्त उसने बोला था व्हाट्सएप उधर मोबाइल से कि मैं 3 दिन के लिए बाहर हूँ, लेकिन इमीडिएटली मैसेज दिया था उसने उसको। आज मैं दोबारा करता हूँ। नहीं तो कहीं और भी देते हैं फिर। यार ये बहुत मुझे टेंशन हो रही है। नहीं है, बात यह है कि उन्हें कितने किए वो रिप्लाई देना, जो भी देगा साला आपको दोबारा नहीं भेजना उसको। ठीक है सर। ये तू यहाँ इंडिया में देख कोई, ये नहीं तो इसी को भेजेंगे हिमाचल वाले को कि नहीं कर पाएगा वो, मंडी वाले को। मंडी वाला तो काफी है ज्यादा, और उसका रिजल्ट भी ना उतना अच्छा है। हाँ ज्यादा देखने की सोच इसमें। हाँ हाँ। ये अमृतसर वाली मैडम थी तो उसका भी कोई लड़का कोई ट्रेन नहीं है बंदा, वो कहती फार्मूला अभी उसको भेजा, अगर वहां से कुछ आया आज मैं उसको मैसेज करूंगा मैडम को। ठीक है। So when two oxygen atoms of the tetrahedra are shared, you get a ring compound. So cyclic compounds in which three tetrahedra or six are sharing their two edges, not two edges, two corners. They are most prevalent. They are most common. So examples are wollastonite. This is calcium Si3. So when there is Si is 3, this is O9. When it is 6, this is 18. 18, and when it is 3, it is 6 negative. When it is 6, it is 12 negative. So 6 O8 negative occurs in beryl. Beryl is an important mineral. We'll talk about that later on. Beryl contains beryllium 3 times, aluminum 3 times, 2 times as in counter cations. And inside we have a ring silicate which has 6 tetrahedras sharing their 2 oxygen corners. So this is one tetrahedra, second tetrahedra, third tetrahedra, one negative charge, 2 and 3, fourth, fifth, and sixth, six negative. Silicon, each tetrahedra is sharing 2 oxygen atoms. So this particular one is sharing one here and one here. This particular is sharing one and one here. So 2 oxygen, 2 negative charge per tetrahedra. So there is there are 3 tetrahedra, therefore 6 negative charge. And similarly here, each tetrahedra is sharing 2 oxygen atoms and 2 negative charge per tetrahedra. Because there are 6 tetrahedra, there would be a 12 minus. So in beryl, this silicon Si6O18 units are aligned one above another. So if you stack rings, these cyclic rings, one above another, inside this a channel will be formed. So in that channel, sodium, lithium, and cesium ions are present, and this makes this beryl very permeable for ions, for small molecules, atoms, for example, helium. And beryllium element, or they are also used as gemstone. Beryl is also an important component of the granite. Pale green crystals, beryl exists in the granites as pale green crystals, which are six-sided. The shape is six-sided prisms, and adamant is same formula as beryl, with the exception that it has additional 1 to 2% of chromium, which gives strong green color to this mineral. Right. So these are cyclic compounds, cyclic silicates. Now chain silicates. Chain silicates are formed, simple chain, these are also known as pyroxenes. Pyroxenes, common name is pyroxene. Two oxygen atoms or corner atoms of the tetrahedron with the other tetrahedron, and you generate a straight chain. Same number of oxygen atoms were shared in the cyclic compounds also, but there you get a cyclic compound. But if the silicates do not form a cyclic compound, they can also form straight chain by sharing two oxygen atoms. So large number of minerals form chains. Variety of different structures are formed because the arrangement of the tetrahedra in space. This one thing is common in all these chains, that they will share two oxygen atoms per tetrahedron, but they can generate different variety of structures because of the arrangement of the tetrahedra in space can vary and repeat units can be different. Most common arrangement in has the most common arrangement of this straight chain silicates have repeat unit after every second tetrahedron. So these are examples: lithium aluminum silicate, which is main source of lithium, magnesium silicate, calcium magnesium. These are dimeric silicates. So these are different ways of arranging silicates. See, every silicate sharing two oxygen atoms with its neighbor, but the repeat unit is different because of the different arrangements of the tetrahedra in this space. In this chain, the repeat unit is this one. After one, first tetrahedra, second one is identical, third one is identical. So repeat unit is this one. But in this case, the repeat unit is after two silicates, two tetrahedra. Then you have repetition. And in this, we have three silicates, repetition after three silicates. Here again, we have four silicates. After four silicates, you have repeat. So here, 1, 2, 3, 4, and 5. So different arrangements of the silicates are possible in space. That gives diversity to the structural features. So we have calcium silicate, three tetrahedra, 4, 5, 6. You can have this much tetrahedra joining together, forming chains. Then we can have double chain can be formed when two chains, join together by the third oxygen atom. In a chain, every tetrahedra is sharing two oxygen atoms with its neighbors, two neighbors. So two different neighbors. Now, the third oxygen atom is also shared with the oxygen atom of the other chain. Then you have a double chain. These double chain silicates are known as NP bonds. There are several ways this thing happens. This is SiO2, Si2O8, and times that 2N negative. These are different formulas. Most common and best known NP-wells are asbestos mineral, which has SiO4O11 and times 6 negative, 6N negative. In these double chains, the sharing of oxygen atom is not common. Some of them share two oxygen atoms, and some will share three oxygen atoms. How? This I have not shown it all. So no. Come here. No. No, I will not try it. We'll do it tomorrow. I will stop here. I will stop here because I don't have
Okay,
this
sir.
structure. I don't have that structure. We'll stop here. We'll meet tomorrow, hopefully. Thank you very much. मुझे जाना है. We'll discuss tomorrow. If you have any question, you can reserve them. Okay?
Okay, sir.
Thank you.
Okay, sir. Thank you.